or is it a physical sky with non-living entities? There are all these questions that are just part of the human experience that comes, and you begin to extrapolate backwards and say, it is remarkable that we ourselves have started as single cellular life billions of years ago and evolved to where we are today, complex life, intelligent life, and life that has the capability to probe the presence of life elsewhere. That's a huge stretch right there. That's a huge advancement. So this is all real. When you're working on this stuff, this is all real. These thoughts come into my mind. So I just want to start by saying there's a huge amount of gratitude for people who have contributed directly or indirectly, but just feeling lucky to be alive at a time when this is happening, regardless of whether it's us or someone else doing it. I'll just say that much up front. Obviously, thanks to my whole team who is here and who are not on the paper, but just as important for our day-to-day activities on various other projects. So with that introduction, I will dive into it. This will be roughly 40-ish minutes if you're calculating how long you need to be here. Talk will be like about 35-40 minutes, and then we'll take lots of questions. But I truly feel, and this is me saying as being in this field for almost 2 decades now, working on basically every first data set from every instrument as far as atmospheric observations is concerned, having developed atmospheric retrievals, looking at the first atmospheric compositions retrieved. From that entire perspective, I feel like what we are seeing is a major paradigm shift in the field of exoplanet science. Even if we just say, we have detected molecules in a habitable zone planet, it may or may not be due to life, forget it, right? Whatever it is due to. Even just the very act that we're able to do it is a huge step. Not everyone may appreciate it because it's more wiggles on a plot, right? Most people may not appreciate it, but from a technical point of view, this is a major leap. And even I myself would not have guessed that even with JWST we'll be here, even just like 3 years ago. Heck, even like a year and a half ago, we wouldn't have predicted that with one JWST observation, you'll get the signal to noise that we're getting here, right? So I want people to appreciate that the technical marvel that these data sets are, okay? So interpretations we can talk about. And then the interpretations are what take it beyond the scope of exoplanet science and broader science and its society in a specific way. So I just want you to have it in the back of your mind, is that the importance of this result is not whether we have found life or not. It's more that we are demonstrating capability to do that. Because the alternative, if you ask someone, usually you get the question, when can we detect life? Do we have the capability? People 5 years ago would have said, no, we'll need 20 years. Here we are saying that it could be any time now to detect these molecules, whether or not they're due to life. And again, that's another technological paradigm shift.
मैं सिर्फ 3 घंटा आपसे मांग रहा हूं. इस 3 घंटे के अंदर मैं आपको एडवांस एक्सेल के फॉर्मूलाज के साथ एआई और चैट जीपीटी हैंड्स ऑन प्रैक्टिस के साथ सिखा दूंगा. तो एक हाई पेइंग सैलरी के लिए
I realize there's a lot of philosophical underpinnings here that I'm going through, but I'm going through them because it is important. It's a very human experience, and we're all in it as a species. So for the longest time, the search for life until a few years ago on exoplanets was focused on looking at Earth-like planets. This is why we are trying to have our detection techniques honed to find smaller and smaller planets, especially around smaller stars, because then the planets are contrast becomes more favorable to observations. Even then, we are realizing that it's very difficult to observe such planets. Even more challenging would be Earth-like planets around Sun-like stars, for which we have no facility currently to detect their atmospheres, right? So that's why we're building or planning to build at least the next generation of large-scale facilities like the Habitable Worlds Observatory and so on. But it is still good to consider that as the holy grail, because that is the holy grail, to find like an Earth twin around a Sun-like star. And just for reference, for people who haven't heard about this already, but the notion of habitable zone is useful. These are not like very accurate representations where those boundaries are, but for the longest time, there has been this notion of the habitable zone where if you put an Earth-like planet around stars of different masses, you want the distances to be just right so you can have liquid water on the surface if you have an Earth-like atmosphere, right? So that's all good. But with those assumptions of the planet bulk properties, the masses, radii, and the temperatures and so on, atmospheric compositions, there is a relatively narrow range of objects you can look at in the search for life. And if you ask today how many such planets are there where we can even follow up with current facilities, there will be like a handful, like 4 or 5 tops with JWST. Even there we have challenges. But what has happened in the last, even the last decade is that we have been detecting lots of planets that are between Earth and Neptune in size. This is the sub-Neptune regime you may have heard of. These are planets which have no analogs in the solar system. They are between Earth and Neptune in size. And there are various theories of how you would explain their interiors, what their interiors could be. We don't have a role model in the solar system. Now, when it comes to the search for life, then the question is, well, can we actually use this population? This is the dominant population within the exoplanet population, right? These sub-Neptunes are the dominant class. The natural question to ask is, well, if we have a small number of planets that are Earth-like and we're finding them hard to observe their atmospheres, can we somehow use this population, intermediate population that we have, and go look for biomarkers there? But then there's the obvious challenge, which is, well, they're not really Earth-like. Do we know if they can be habitable? So these were the questions that have been making the rounds in the field over the past decade or so. And what we did 5 years ago is branched out slightly and asked a slightly different question. Well, why don't we make just a hypothesis testing argument, right? Let's just assume that some of these planets that can be significantly larger than Earth are habitable. And let's find out what are the conditions that you need on such a planet for it to be habitable. It's an interesting exercise. You should try it at home sometime, because I did it in my Part 3 course this year. I said, in the course I say, all the, we go through atmospheric properties and interiors and so on, and I gave a very simple question. I said, just consider the planet mass, the planet radius, and the atmospheric composition, and build me a planet that you think that is habitable, a hypothetical planet, and that you would think would be most conducive to observations. That is the important bit. You're given a facility is fixed. Let's ask ourselves, what is the kind of dream planet that you would build with all those properties, like with a certain mass range, radius range, and temperature range, and an atmospheric composition? And interestingly enough, the students in my class actually came up with a Hessian world. They didn't think that that wasn't the concept, but that is what they came up with. They said, for the planet to be observable, you need a large radius, you need low density, basically, and you need a hydrogen-rich atmosphere, which increases your observability because the scale height is larger, so you can observe it better. All of these properties are basic first principle properties. It's just that no one in practice looks at things that way, right? No one says, I have a telescope, let me build a planet. No one says that. People will say, we know we want to look for planets like Earth, so let's build a telescope, which is much more expensive, by the way. So I think that was the radical shift. It starts with a very simple question, and that's the question we asked 5 years ago. Let's build a planet. Let's hypothesize a planet and see where that planet lands. And it lands in the sub-Neptune regime. And anyone can do that exercise. And it started with this planet sub-Neptune K218b. It is a planet with about 8.6 times Earth mass, 2.5 times Earth radius, and it's in the habitable zone of its host star. This was between 2015 and 2019. There were a number of observations that confirmed the bulk properties. And at the time, no one would think of this planet as habitable because it's 2.5 times Earth radius, and there is no concept of such planets being habitable. This was called a mini Neptune, which is you take Neptune, miniaturize it, you have a deep H2-rich atmosphere. The pressure and temperature at the bottom of that atmosphere would be too hot for life. Okay? So it was a mini Neptune by most assessments. So we said, let's actually try it out. Let's look at it, build some internal structure models, and see if there is any chance that it could be anything other than a mini Neptune. So we took the atmospheric observations, the very first HST observations that were available at that time, so that was an HST spectrum. And the posteriors you see are the constraints on the atmospheric abundances, and people had claimed this was H2O. We also found that it could be H2O that's causing that feature, but there were other studies which said that it could also be due to methane, so there was degeneracy, or it could be just star spots causing that feature. So it wasn't known exactly what that feature is telling us, but we went ahead and did internal structure models. This is where these are mass-radius relations of constant compositions, iron, silicate, water, and so on. And you mix these in different proportions to build a planet and see if that matches your observed density, the mass and radius constraints. And we found that indeed most of the solutions do satisfy a mini Neptune scenario, but there are also other scenarios that can work, which is like the rocky world scenario, or other words, a gas dwarf where you just have a rocky planet and a thick hydrogen-rich atmosphere, or a mini Neptune, like Neptune, has a lot of volatile content in the interior, ices and high pressure ices, and a hydrogen-rich atmosphere, or a third alternative which hadn't been considered before, which was a water world with a thin hydrogen-rich atmosphere. Ocean worlds had been thought of before, but with different kinds of atmospheres. But here, our motivation in my group, usually we do deep end theory, but we are also always looking how can we observe things. So with that flavor, we could come up with this alternative as well. And then if you look at the equation of state of water and plot the temperature and pressures allowed at the boundary between the atmosphere and interior of such a model, those are the loci, the red curves there you see. And you'll see that most of those points along the red curve fall in the supercritical, in other words, high temperature water state, which won't be habitable, but a very small fraction of those solutions do allow for liquid water. Okay? So no one would go ahead and say this planet is habitable for obvious reasons, right? Most of the solutions don't allow that. But what we found is that there is a chance, there is a small number of solutions that do allow for liquid water. Okay? So as a full-time theorist at that point, I said, why don't we take this solution and build more planets like this and scan the whole parameter space of mass and radius and see how many other planets are out there which can satisfy these constraints. So this is when we came up with this concept of Haitian worlds. These are planets which would be covered in oceans and have thin hydrogen-rich atmospheres. At that time, it was just a theoretical concept. And then we found that there is a big range in masses and radii, all that cyan region, where you could have habitable conditions on the surface.
Albert School is within the academic world what Edmond de Rothschild is within the world of finance. This is about being disruptive, changing the rules, being conviction-led with a very clear purpose. And this is about looking for impact. My name is Stéphane Voyer. I have the privilege to be the global head of human resources for Edmond de Rothschild Group. If we want the leaders of tomorrow to properly lead the world and the industry and the business, we need to make sure we rely on.
So planets as large as 2.5 times Earth radii, Earth size, could also, in principle, be habitable by this metric. So similarly, in addition to size, there is also a much larger range in distances from the host star, where you can also have habitable conditions for such planets. I must say that a lot of this, just as for the terrestrial habitable zone, involves a lot of assumptions. What albedo that you're assuming? Albedo is how much reflection you're getting from the planet, so it decreases the amount of starlight you get. All of these, you have to make some assumptions when building these models, but the basic premise is that it increases your habitable zone significantly. So we came up with this concept of Haitian worlds. And then we said, let's try it out observing these objects. Now, this paper coincided with the launch of the James Webb Space Telescope. This is all happening coevally. So this was 2021, and JWST was launched in 2021. And we had put in a proposal already before JWST launch, obviously, to observe this planet in the first cycle. So JWST obviously came, started revolutionizing the field with the first observations. So this is, I'm showing you some observations of hot Jupiters, hot giant planets. The very first observations, you see the spectacular spectral features at very high signal to noise. With the very first observations, you detect lots of molecular features at high precision, this and that. This is not about K218b, this is about hot Jupiters using the transit technique. Okay? So it started revolutionizing this field like almost immediately. So for those who are not familiar with this technique, I'll just say in 1 minute what transit spectroscopy is. So you're seeing the planet going in front of the star. So some of the starlight is going through the atmosphere of the planet before reaching the observer. Okay? So the spectrum of the star passes through that filter, that's the atmosphere, and has imprinted on it the spectral absorption features due to the planet's atmosphere. Okay? Now, if you take that, and then you take another situation where the planet is not in front of the star, you just get the stellar spectrum. You take the difference between the two, you can isolate the absorption that's happening in the planet's atmosphere, right? And from that, and that's what you're seeing in these plots. The transit depth is basically absorption in percent, okay? And you can see the fingerprints of various molecules that you can see even by eye in these figures. And because those we know from Earth-based experiments what those molecular features should look like, we can interpret this data very easily. Okay, so now with that sort of background, so that was our theoretical motivation so far, how we came up with this class of planets. This was purely a thought experiment until then. So then we proposed for JWST observations, and I'll give you a bit more detail on the observations, but I just want to drive home the point that this was the HST spectrum in the pre-JWST era. It's useful to remember one's humble beginnings, as in most things in life. This is where we started 5 years ago, and we were not sure what that feature was due to, as in the field. And that was obtained with over 60 hours of HST time, Hubble Space Telescope time, a lot of time. And then we got our JWST program approved. This was a program where we said our aim was not to detect biosignatures at all. All we said was that this is an interesting planet. We want to search for disequilibrium chemistry in its atmosphere, because for small planets, you expect the atmosphere to be out of equilibrium due to various processes. So we asked for 3 observations, NIRSPEC, NIRIS, and MIRI, spanning the full wavelength, roughly the full wavelength coverage from like 1 to order 10, 12 microns. And we were being conservative, saying that, okay, the signal to noise, we expect it to be pretty bad at longer wavelengths. So we are really counting on just 1 to 8 micron, and these 3 instruments will give us that, okay? And then the present,
I'm jumping ahead a little bit. So I'll show you what we got with the NIRIS and NIRSPEC observations previously, but that's showing a transit from the present observation, the MIRI observation. You can see how clean that transit is, right?
Very high signal to noise. So